Hello and welcome to another review session for the final exam in Calculus 3208 presented by CDLI. Today we're looking at applications of differentiation still, and we're well on into that unit now, and we're looking specifically at how we apply calculus to sketch graphs of polynomial functions. So we've done most of the legwork for all this stuff so far in terms of understanding how we get there. Now we just sort of put it all together. So we're going to determine some important features from the graph, and then we're going to learn how to sketch our graph based on those features. Alrighty. So here are some of those important features that we have to come up with. We need to get y-intercepts, of course, and we do that by letting x equal 0, and then we solve for the value of y, or actually just evaluate. And to get the x-intercepts, we let y equal 0, of course, and then we solve for the appropriate value of x. To get maximum and minimum points and our intervals of increase and decrease, these go together, we need to look for our critical values. And once we have our critical values, what we need to do is look at our first or second derivative test, or what we can do is just look at intervals of increase and decrease by using f prime to determine where we're increasing and decreasing. And after we got that, we just need to get our y values for those points as well. And for the last two that go together here, for inflection points and intervals of concavity, we look for hypercritical values, which are values where our second derivative will be equal to 0. For polynomials, it'll never be undefined, of course. It'll either be equal to 0 or out to lunch entirely. And then we're going to go for intervals of concavity, and we use f double prime to find out where it's positive and negative, and that tells us whether we're concave up or concave down. So let's put all that together. We'll start with a simpler example where most of the work has been done, and we have to make a rough sketch. So in this case, we're given some information about the derivative of a function on several intervals. And I'm going to draw a number line first. That's the way that I put these things together. And we'll see that we have at x equals -1, +1, and +3, things are changing. So at -1, +1, and +3, we have our critical values here. And what we have to determine is what's happening in between those values. So we look at the sign of f prime and see what that means for f. So on the first interval from -infinity up to -1, we see f prime is positive, so f is increasing. And on the interval from -1 up to +1, f prime here is negative, so that means that f is decreasing. And then from 1 up to 3, we're negative still, so we're still decreasing for the original function f. And then after 3, and from there on forever, the first derivative is positive. So if that's positive, then our function increases out there. Okay, so let's see what that means for our critical points. It means that at x equals -1, since we increase and then decrease from one side to the other, we're going to have a relative or a local max value here. And at x equals 3, since we decrease and then increase, we're going to have a local or relative minimum value there. Oop, that's an end. Okay, now, x equals 1 is a little bit of a different story since our function is decreasing, and then we have a slope of 0 at 1, and then it decreases again. The only thing we can think of for that would be a graph that decreases, and then it's going to have to level off to have a slope of 0, and then begin to decrease again. So we have this kind of funny thing happening at that point. So it does have a horizontal tangent, but it decreases on both sides. It will be neither max nor min. It's just this kind of a funny shape. We're going to see what happens now when we put it all together. So they don't give us any y-coordinates for our graph, so we'll just figure out whatever we like here. And at x equals -1, that's a relative max, so we'll put that up there somewhere. And at +3, it's a relative minimum value, so we'll put that one down in the netherworld. And then at x equals 1, where we have that funny bend in the graph, we'll put that point, I don't know, right about there. All right, so I need to draw a curve that reaches a maximum value here at -1, and then it's going to decrease this way, flatten out at +1, but then start to decrease again, and then bend upward at 3. So we have a max here, we have a min here, we have neither, but we still have a cool critical value right there. All right, let's apply this to a real example where we actually start with an equation, find out all the detail, then put it all together to make a graph. Alrighty, so first couple of things we need are our intercepts, x and y. So we'll break this into 3 groups. To get our intercepts, start with x-intercept. We'll let y equal 0. So our equation becomes y equals 0 cubed minus 12 times 0 squared plus 36 times 0, which is a whopping 0. So since our y-intercept is at 0, 0, that's on the origin, so that's got to be one of our x-intercepts as well, because the origin is also on the x-axis. All right, so let's check out for our y-intercept and see what we get there. Whoops, that's what I just did. Y-intercept, excuse me. Now I'm looking for x-intercepts. Okay, so to get our x-intercepts, I'm going to whoops, and up here, look, I even wrote y equals 0. Yuck, not awake yet, I suppose. Now I'm going to do my x-intercepts by letting y equal 0. So I have 0 equals x cubed minus 12x squared plus 36 times x. Okay, so what I'm going to do now is try to factor to solve this equation. Got x outside of x squared minus 12x plus 36. And we can factor that again and have x minus 6 times x minus 6. And so we get roots there at 0 and 6. And both of those are kind of special. The first one at 0 is special because, hey, look, we already had that. It was our y-intercept too. And at 6 and 0, that's also going to be a special one because it has this squared hanging around. So that's a root with multiplicity too, which means it's most likely going to give us an intercept that's also a maximum or a minimum value. So we'll see what happens when we actually go sketch a graph of that. Okay, so now that we've got all that figured out, let's clear some space out of the way here so that we can go ahead and work on the rest of this problem. Alrighty, here we go. So the next thing we have to get are our maximum minimum values, and as well, we need our intervals of increase and decrease for this function. So to get our maximum and minimum values, we know we're going to need critical values first. So to get our critical values, we're going to need our derivative, dy by dx. And dy over dx is going to be equal to 3x squared minus 24x plus 36, just using the power rule on every term of our polynomial. So we let that equal 0, since it's never going to be undefined, of course, it's polynomial. And we just solve this simple polynomial equation, which is a nice quadratic, common factor of 3 first. Don't even need to keep that around since we're equal to 0. We can eat the 3. So x squared minus 8x plus 36 divided by 3 is 12. So that's going to give us x minus 2 times x minus 4. So we're going to get critical values at 2 and 4. So over here we can say when x equals 2, we're going to have some y value that we don't know yet. And when x equals 4, we'll have another y value that is yet to be determined. What we have to determine now is what those y coordinates are. So I say y equals 2 cubed minus 12 by 2 squared plus 36 times 2. And we'll put all that together. We have 8 minus 4 times 12 is 48 plus 72. So that's going to give us a lovely 32 altogether, I believe. So we've got 2 and 32 will be one of our critical points. And when x equals 4, we're going to have y equals 4 cubed minus 12 times 4 squared plus 36 by 4. And that's a little harder to do in your head, but let's see if we can't figure that one out as well. And hang on, if you haven't noticed my mistake here, you're making as many as I am, I suppose. Right here, this 4 should go away. 2 times 4 is 8, not 12, and they add up to negative 6. That should be a 6 there. Yipes. So our 2 critical values are actually going to be at 2 and 6. Should have known that because we already stated we were expecting one at 6, didn't we? All right, so we'll cross this out and just redo that part. So it'll be 6 cubed minus 12 times 6 squared plus 36 times 6. And there's absolutely no arithmetic to do because we already know that when x equals 6, y equals 0. So there's our other critical value. So we've got critical points at 2 and 32 and at 6 and 0. So now we need to find out where this function is going up and going down so we can figure which ones are maximum and which ones are minimum. So we'll once again clear a little space. We can get all that taken care of. Okay. So let's draw a number line. And that'll allow us to test for intervals of increase and decrease around our critical values, which are at 2 and 6. So here's 2, and here's 6, and let's check all this stuff out now. So on the first interval, I don't know, maybe x equals 0 will be a good point to test. And we're going to look at f prime and what it means for f of x, the original function. So when x equals 0, f prime of x we already know is equal to, we don't know, sorry, I got to write it out here. So y prime is going to be equal to 3x squared minus 24x, yipes, 24x plus 36. Okay, so at 0, that's going to have a value of positive 36. So we're positive out here, which means the original function starts by increasing. Then in between those 2 points, we'll choose a value like, say, 3. And if I plug 3 into my equation for y prime, I've got 3 times 3 squared minus 24 times 3 plus 36. And when we work that out, we should get a number that's a negative, and we do, so that turns out to be a negative number. So we're negative in here, which means our original function is decreasing. And then after that, we can try a number like 7, so 3 times 7 squared minus 24 by 7 plus 36. And that gives us a nice positive answer, so we get a positive out here. And we can see now the increasing and decreasing behavior of our function. So this function is going to increase on an interval that starts at negative infinity, and it's going to go all the way up to and stop at positive 2, not including the 2. And it's also going to increase on an interval that starts at positive 6 and goes all the way out to positive infinity itself. And it's going to decrease in between those 2 intervals on the interval that starts at 2, not including, and goes up as far as 6. Now you'll notice that we're not including any endpoints in our intervals of increase and decrease. And that's an important point because we should know that the derivative is actually 0 at those places. So we're neither increasing nor decreasing. All right, so now that we've got our increase, decrease, max, min business all taken care of, we can move on to our inflection points. We should make a note, though, that which ones are maxima and minima. This one's going to be a max, and this one's going to be a relative min. So over here we can say that guy's a max, and that one's a min, and we probably could have guessed that anyway based on the y-coordinates that we had. All right, so let's get rid of all this stuff and make some room for the inflection and concavity business. Okay, so to find points or possible points of inflection, we've got to get our hypercritical values, and they are places where the second derivative is either 0 or undefined. This is polynomial, so it can't be undefined. We'll have 6x minus 24 as our second derivative. We set that equal to 0. We have 6x minus 24. So x is going to be equal to 24 divided by 6, and that's going to give us a value of 4. So we're going to have an inflection point most likely here when x equals 4. We need to know its y-coordinate, so let's find that. Y at x equals 4 is going to be 4 cubed minus 12 by 4 squared plus 36 times 4. And we put all that stuff together, and we're going to have to come up with a really nice number like 16, I believe. So we put all that together, and we get an answer of 16. So at 16, or for y and 4 for x, we're likely to have an inflection point. Let's check our concavity and make sure that all that works out. So all we have to do now is a concavity test. Just going to erase all that business again. This will be the last detail we need to get before we actually get down to sketching a graph. So for our concavity test, we're only going to plot one hypercritical value, and that HCV is going to be at x equals 4, and we'll test either side of that with our second derivative, f double prime, and see what it means for our original function f. Now let's keep in mind that our second derivative was 6x minus 24. It's an important thing not to forget. So if we try a number like 0, we find out that it's negative over here, and if we try a number like 10 billion, we find out that it's positive on this side. So what that means for our original function is that we're concave down, and then we are concave up. Oh, I don't like to be concave down. Yay, I like to be concave up. Okay, so now we can say that we're going to be concave up on the interval x starts at negative infinity and goes all the way up to 4. And we're going to be concave down on the interval that starts at 4 and then proceeds on to positive infinity. Okay, so that's all the detail. What we're going to have to do now is make a sketch of this graph. So I'm just going to jump slides here for a sec. And what I've done is I've reproduced all of that information that we just found out over on the right-hand side. And so it's a lot neater than I can do with my handwriting. And now what we have to do is take all of that and plot it on a graph. So let's get down to business. First things first, our origin was both our x and one of our x-intercepts and our y-intercept. And we had this point over here at 6 and 0, which was a local maximum or local minimum value, and it was also an x-intercept, and at positive 2 and positive 32 for y. So let's see, our scale here is 5 units per block, so a little less than half a block for 32. Will put us right about here to get our local max value. So we've got a max there. We've got a minimum here, which doubles its life as an x-intercept. And we have a point of inflection at 4 and 16, so slightly above that line. And when x equals 4, we have to inflect our concavity. So we should be concave down on the left side and concave up on the right side. And that seems to jive with what I'm thinking this graph is going to look like. So let's see if we can sketch this graph now. So I have to draw a curve that comes up this way through that y-intercept, hits a maximum value up there, comes down to here, and then inflects its concavity, bounces off at that point, and that's going to be our minimum. Now this graph should be nice, evenly smooth curve here, but I'm not exactly the most artistic when it comes to these things, as any of you who've been watching all of these videos probably know already. However, you get the idea. It's a little bit scary. Look, it's a ghost. Woo! Okay. All right, let's move on to the next one. In this case, we have the OR term problem. So it's basically the same procedure as always. Sketching the graph of a polynomial, finding all the details. If you want to pause the video at this point and work it out, go ahead. But I'm going to flip to the solution side. And so here's the solution for all that. All the details that we found and all the gory details of how you work those things out. Tells you all the stuff. And then on the next page will be the graph. So here's the graph based on all of those details that you can find out for that particular function. Let's highlight some of the key ideas here, shall we? First of all, we find our y-intercept, remember let x equals 0. X-intercepts we solve, f of x equals 0. All right, we solve to get our critical points, our possible max and min, by getting our critical values when the derivative is 0, and then find the y-coordinates in the original equation. Find our intervals of increase and decrease using a test with f prime. And we find our hypercritical values to find possible inflection points, get their y-coordinates. And then we use an interval test with the second derivative to find concavity. And that should about cut it. So that's all the quick and easy details for a quick review of how we sketch the graph of polynomial functions using some calculus. Happy studying and all the best on your exams.